I hope all is well for you. Today we will see, will the cosmic microwave background radiation run out one day? Welcome to the Question Answer channel, the channel where you will find the answer to everything. Today the answers will be presented by Viktor T, Toth, McLennan, Tobjorn Larson and Dane. We will start with the first answer of Viktor T, Toth.
Yes, gradually, very gradually. Think how the CMB was produced. Roughly 385,000 years after the earliest known epoch in the existence of the universe, the cosmos was still filled more or less evenly by a mixture of mostly hydrogen, some helium, and trace amounts of other elements. It was a hot gas with a temperature of about 3000 K, ionized and glowing. But it was also not transparent, so any light it produced was reabsorbed in short order. Over time, the density and temperature of this gas was decreasing to the point when finally, positively charged atomic nuclei and negative electrons began to recombine into neutral atoms. As this happened, the gas was gradually becoming transparent, so its own residual glow now had the freedom to travel. As it became transparent, it also stopped glowing, but there was a brief transitional period when there was still enough glow yet the medium was sufficiently transparent not to reabsorb all of it. The result, at this point in time, light was produced at every location in the universe, traveling in every possible direction. Now fast forward to the present. You look at the deep sky, beyond the most distant stars and galaxies, and what do you see? This glow. Because of the expansion of the universe, the wavelength of this glow has increased by a factor of approximately 1100, so instead of the yellowish-white glow of an incandescent gas at 3000 K, we get minuscule amounts of microwave radiation corresponding to a cold background at 2.7 K temperature. But it is detectable by a modest radio telescope. Okay, so we look today in a specific direction and see this glow. When we look in the same direction tomorrow, what do we see? The glow is still there, but the gas we saw yesterday now appear completely transparent. The glow we see today comes from a slightly more distant spot in the universe situated behind the spot that glowed yesterday. And so it continues, each and every day we see this glow coming to us from an ever so slightly more distant location. Of course the universe is vast, so a difference of 1 day, 1 year, even a million years doesn't matter. But billions of years do. Many billions of years from now, the CMB will come from vastly more distant corners of the universe. This means that it will be redshifted even more, and it will also be weaker. So yes, over time it will fade. From microwaves, its wavelength will shift to UHF, then shortwave, then longwave radio. Its intensity will continue to decrease. So future civilizations, hundreds of billions of years from now, may not even be able to detect it anymore. Makes you wonder how, or even if, they will understand the nature of an expanding universe without such a key piece of information, and makes me wonder anyway, if there were similar key pieces of information in the past to which we no longer have access. If you find my posts useful, please consider supporting my efforts.
The following answer is from McLennan.
The cosmic microwave background has been shining continuously everywhere in the universe since it was first formed about 380,000 years after the beginning. At this point, the universe cooled enough for electrons and nuclei to combine into neutral atoms. This process is called the period of recombination. Before that epoch, every photon that formed was quickly scattered by a free electron. But after the electrons had mostly combined into neutral atoms, whatever photons were flying around at that point just kept on going. A few of them have hit atoms and been absorbed during the billions of years since, but most of them are still making their lonely ways through space. A photon that passes through an isolated neutral atom out in space is not likely to be absorbed, unless it has exactly the right amount of energy to excite an electron to a higher orbital. From that time until the present, everywhere in the universe, photons from that period have been continuously passing through. Because of the continuing expansion of the universe, wherever in the universe you are located, there are plenty of other locations that are exactly as far away from you in light years as the number of years that have passed since the period of recombination, and the photons that were born in those parts of the universe are reaching you now. In fact, as long as the universe lasts, there will always be photons that were born somewhere else during the period of recombination and have had just enough lifetime to be reaching you now. The universe is expanding fast enough that there will never be an end to this phenomenon. Of course, we are moving away from the matter that originally emitted these photons at an enormously fast rate, due to the universe having been expanding for 13.8 billion years now. So from our frame of reference, their frequency is downshifted enormously. This radiation started out with its spectral peak at about 3000 degrees, which is about the same temperature as a light bulb filament. Had you been alive and floating in space during the period of recombination, you would have perceived space around you to be glowing as if it were all filled with light bulbs. But when these photons reach us, due to the velocity difference, they are redshifted down so far that their spectral peak is at about 3 degrees. This is deep into the range we call microwaves, which is why we speak of the cosmic microwave background.
What do you think? We will continue with Tobjorn Larson's answer.
Q. Will the cosmic microwave background radiation run out one day? The cosmic background spectra today, a blackbody emission that peaks at 3K. An X emission. A. As the universe expands, the photons of the cosmic background will continue to be dispersed and redshifted towards lower energies. The initial photon emission had a blackbody emission temperature of 3.000 K and has redshifted with a factor of Z equals 1.000 to a 3K radiation. Eventually the photons will be so weak. Access this answer and support the author as a Quora Plus subscriber. Access all answers reserved by Tobjorn Larson. For Quora Plus subscribers, access exclusive answers from thousands more participating creators in Quora Plus. Browse ad-free and support creators. Start free trial. Learn more.
We continue with Ryan Dean's answer.
I would assume because it's a flat representation of spherical information. Though, I don't know why they don't choose one of the other potential projections from time to time. If you look at it, you can see the distortion especially near the edges. Similar to this Apian 2 map projection.
The video is over, thank you for staying until the end. I hope the video has you more, if so you can subscribe and activate the bell to miss any video. Also remember to leave a like. We are coming to the end of this video, share your views on this question in the comments. See you next time.